Hello class. So this is Math 1440 and I'm going to go over section 8.3. Before I do that, let me just remind everyone our first test, exam number 1, is going to be Friday, September 18th of next week. Friday, September 18th. And that will be taken on WebAssign. And you can start anytime before 10 p.m. And of course, it's going to be open book. And calculators are allowed. And just so there's no confusion, we do not use webcams in this class. So you do not need a webcam on your computer. No webcam. Okay, so this section 8.3 talks about the second derivative test. And there's no need to memorize the second derivative test. Again, the test is open book, so have all this handy. So that way you don't waste time looking through everything. Okay, so here is the second derivative test. D of x comma y, which is going to be your critical point, is going to equal, and you input the critical point xy into your second order partial derivative f sub xx, multiply that by f sub yy, evaluated at your critical point x comma y, and then it's going to be minus the square of the mixed partial, evaluated at your critical point x comma y. So let me step back so you can see it all at once. Okay, and I wrote note. We need to find 3 second order partial derivatives for this second derivative test. You know, there's f sub xx, that's the second order partial derivative, f sub yy, and f sub xy. So ultimately, we're going to have to get second order partial derivatives to use this test. And of course, before you get your second order partial derivatives, you need your first order partial derivatives. Alrighty, so, and then once you get your result from the second derivative test, one of 4 things you have to look at. So one of 4 cases will apply. If d of a comma b, your critical number, is greater than 0, and the second order partial derivative f sub xx evaluated at that critical number is less than 0, if both of those are true, then we can conclude that we have a relative max at that critical point. And then these are the other 3 here. You can look at them from your notes, which is on Learn. Okay, so when you're asked to find relative extrema, I mean either maxes or mins. So relative max, relative min, that is the same thing as saying relative extrema. For a function in 2 variables, what you want to do is first find the critical points of your function in 2 variables by solving this system of equations, your first order derivatives equaling 0. And then apply the second derivative test. So let's take a look at an example. Example, determine the relative extrema, which means, maximum / minimum, of f of xy equals, and here's our function in 2 variables, xy plus the natural log of x plus 2y squared. So for a solution, remember that all extrema live at critical points. If you're going to be an extremum, that means you're going to be at a critical point. And remember, when you find your critical points, they must be in the domain of your function. They have to be in the domain of f. So always make sure when you get your critical points that they are in the domain of f. If they are not in the domain of f, just reject them. They are not critical points. Because to be a relative extrema, you got to be on the graph. Okay, so now I'm going to get my brother here, and he's going to take me doing this problem. So Doug, okay. Okay, so here we go. First step is to find the critical points. And the way we're going to do that is by finding these first order. Remember, critical points occur at, let's see, what am I trying to say? Yeah, the extrema occur at the critical points. The way you find your critical points, in Calc 1, it was setting the first derivative equal to 0, or see where it's undefined. And similarly, we want to, in the function in 2 variables, you want to set those first order partial derivatives equal to 0, and then solve that system. So let's find the first order partial derivatives. So the first partial derivative of f with respect to x. So here's my function that I'm looking at right here. So to find the derivative with respect to x, just go term by term doing these derivatives. So what's the derivative of the first term with respect to x? It's this constant y. So just write y. Think of y as like a 3. What's the derivative of 3x? 3. What's the derivative of xy with respect to x? The number that's being multiplied next to it. So I get y plus, what's the derivative of ln of x with respect to x? It's going to be 1 over the argument, 1 over x, times the derivative of the argument, but the derivative of x is just 1. Plus, what's the derivative of this term with respect to x? Well, this is a constant term, and the derivative of a constant is 0. So this is it for my first order partial derivative. Because I know eventually I'm going to have to do f sub xx, it's easier if I rewrite 1 over x as x to the negative 1. So this is the same thing, y plus x to the negative 1. I'm doing that just because this is more derivative friendly when I get to my second order. Okay, let's find the other first order partial derivative. So you go to your function and just take derivatives. If you have a sum, the derivative of a sum is the sum of the derivatives. So the derivative of the first term with respect to y is going to be that constant x. This is just going to be a constant. There is no y. So this is the derivative of this term with respect to y is 0. And finally, the derivative of 2y squared with respect to y by the power rule. 2 times 2 is 4y to the first. So I'm just going to write plus 4y. Okay, so now that I have those first partial derivatives, we want to solve this system of equations. Y plus, I'm going to choose the 1 over x for now. Set that equal to 0, and then we want to also write the other partial, first order. X plus 4 over y equals 0. So that's how you find your critical numbers, your critical points. You set the first derivatives equal to 0, partial derivatives, and then you solve the system. So if I look at this first equation, I'm going to solve it for y. If I subtract 1 over x to each side, I get y equals negative 1 over x. And now let's use this for this y here. So I'm going to solve the system by substitution. Substitution. So let's look at the second equation. And I'm going to write x plus, instead of writing 4 times y, write 4 times negative 1 over x equals 0. So the whole point of substitution is to go from 2 equations with 2 unknowns to just 1 equation, 1 unknown. So this is nice. I'll write a smiley face here. We got 1 equation with 1 unknown. Simplifying, I get x, and then plus times a minus is a minus. 4 times 1 over x is just 4 over x equals 0. Let's clear the fractions. Multiply everything through by x. So x squared minus 4 equals 0, because this x cancels with the x. So if I multiply everything through by x, this is what I get. Here I can either factor x plus 2, x minus 2, or I'm going to just add 4 to each side. X squared equals 4, so x is equal to 2, and x is equal to negative 2. So these are going to be the x values of my critical points, but look at this. Can x equal negative 2? Remember, you have to be in the domain. Look at ln of x. You know you can only take the log of a positive number, so x equals negative 2 is not in the domain. So reject. Yeah, bless you. So reject x equals negative 2. So now that I know x is equal to 2, this implies that y, the y coordinate of the critical number, is going to equal, and what you do is you let x equal 2 into either one of these original equations. It doesn't matter. So actually I'm going to look at this one right here because it's solved for y. Isn't y going to equal negative 1 over 2? Because x is 2, so y equals negative 1 over 2. And I would get the same answer if I plugged in x equals 2 here, for example. 2 plus 4y equals 0, 4y equals negative 2, y equals negative a half. So same, it doesn't matter which equation. So let me write this critical point because this is key. We only have one critical point. If we had 2 critical points, we'd have to input the first critical point into the second derivative test and then input the second critical point into the second derivative test. So we would have to do it twice over. But we only have 1, so that's going to save a little time. So x we said was positive 2, y is a negative a half. So there's our critical point. Okay, now let me get my eraser here, and I'm going to clear some space. I want to keep this second derivative test. Hey, Dubby. Good boy, baby. Oh, you good little boy. What a handsome little doggy you are. Good girl. Good girl. Okay. All right, so that's Duffy. All right, so now that we have our critical points, what do we want to do next? We know that we only have one critical point. So we want to input that into the second derivative test. But before we do that, we have to find now the second order partial derivatives. So let's do that up here. We already got our first, here's my first order partial derivative. So if I know this f sub x, I'm going to write it like this. Then here is f sub x. This is a second order partial derivative because you see two subscripts. So what is the derivative? So remember, what this means is you go to your first order partial derivative with respect to x and then find the derivative with respect to x. So here's my first partial derivative of f with respect to x. I'm going to look at this form. What's the derivative of this with respect to x? This is going to be 0 because it's just a constant term. This is going to be minus 1x to the negative 2, which is minus x to the negative 2. I'm going to write that as minus 1 over x squared, rule of exponents. X to the negative 2 means x squared on the bottom. So, okay, let's find this partial now. F sub y with respect to y. How do I know I need these second order partial derivatives? Because they're in the second derivative test. So we go to our first order with respect to y and then differentiate with respect to y. So here's the first order with respect to y. When I differentiate with respect to y, this is just going to be 0 because this is a constant. There is no y's. Here the derivative for y with respect to y is just 4. Just 4. So this is interesting. Notice this second order partial derivative is variable. So we got to be careful. This is beautiful. When you have a second order partial derivative that's a constant, and then that means no matter what you evaluate this second order derivative at, no matter what the critical point is, the answer is always going to be 4 because there is no variables in here. So you'll see what I mean later. Okay, and now I need the mixed partial. So let's do that. F sub x with respect to y. So we go to f sub x and differentiate with respect to y. The derivative of y with respect to y is 1 plus, and this is just going to be 0. So just 1 is the answer. Okay, this is good. So now what I want to do is use the second derivative test. So here we go. We're coming up to our final answer soon. So our critical point we said was 2 comma negative a half. So for x, we write 2. For y, we write negative a half. And that's going to equal, and now we want to evaluate this second order partial derivative at the 2 comma negative a half. So notice f sub xx is negative 1 over x squared. So let me take my time here. Sorry this is a little cluttered here. But I want to do f sub x. I want to find out what is f sub xx at 2 comma negative a half. And that's going to equal, so I input this point into this expression. So it's going to be
negative 1/2.
Yeah, negative 1/2. Thanks, Doug. Negative 1/2. Thank you. So notice that x is 2, y is a negative half. Wherever I see x's, I'm going to write 2's. Wherever I see y's, I'm going to write negative a half. Notice there is no y here. No y at all. So this negative a half is not going to come into play at all. So the answer is going to be, and keep this form, negative 1 over, instead of x, write 2 squared, which is a negative 1/4. So f sub xx evaluated at the 2 negative a half is a negative 1/4 times f sub y evaluated at my critical point. It doesn't matter what I evaluate it at. The answer is always going to be that constant 4. So that's a lot easier. Minus, and here again, the mixed partial, we got to square it. I evaluated at that critical point. But what is f sub xy? It's just a constant. So what's 1 evaluated for any xy? It's just going to be 1. And then we got to square the 1. So minus 1 squared. Okay, so let's see what we got here. Negative a fourth times 4 is a negative 1. Minus 1 squared is 1. And then we get a final answer of negative 2. So now that we have our answer from the second derivative test for our critical point, we can now look at these 4 conditions, which you should have written down for your test. You don't memorize this. Okay, so notice our second derivative yields a negative result. This is the only one. If your second derivative test evaluated at your critical number is less than 0, meaning negative, then that implies we have no relative max or min, but we have a saddle point. So my final answer is saddle point at the critical number, at the critical point, 2 comma negative a half. Sometimes you'll see it written like this. What is the actual point on the surface? Because this graph, if you graph this function, you get some surface. So what is the point on the surface? It's going to be, or you can say at the point on the surface, at the point x is 2, y is a negative a half, and then z, x, y, z. Z is going to be f of this critical point. So go to your function f. So what is f of 2 comma negative a half? Is going to be x is 2, y is a negative a half. What's 2 times negative a half? That's negative 1. Plus ln of x, x is 2. So that's going to be ln of 2. That's just some constant. Plus 2 times y squared. Y is a negative a half. So 2 times negative a half times negative a half is a positive 1/4. And I know 2 times a fourth is 2/4, which is a half. And what's negative 1 plus a half? It's a negative a half. So it's going to be negative a half plus the ln of 2. So that's the a point on the surface. So depending on what the directions say, usually this is good enough. Just say at this critical point, that's where the saddle point occurs. And by the way, what is a saddle point? It means it's not a relative max, it's not a relative min. In other words, there's points in the area that are higher and lower than that saddle point. Okay, so we're done.